I welcome you all to another video tutorial section on finite element procedure for solving structural engineering problems. In today's video tutorial, I'm going to solve this problem on the Ansys program. In my last video, I solved this problem using finite element procedure on MATLAB. I explained the theoretical background of finite element procedure for beam analysis in my last video. In today's video, I'm going to use the Ansys program to solve this problem. Ansys program is a very powerful tool for solving beam problem. However, it has one deficiency right now. The Ansys program, the structural load you can specify on your structure is only the uniformly distributed load and the point load. For other type of load like triangular loading, currently you cannot specify triangular loading on the Ansys program. It's an aspect of the software I think the Ansys software developers need to work on. On the Ansys program, there are three methods of analyzing beam. We have the one-dimensional finite element method, we have the two-dimensional finite element method, and we also have the three-dimensional finite element method. In today's video, I am going to use the one-dimensional finite element method to analyze this beam problem. At the end of the video session, we shall visualize the deformation of our beam. We shall have deformation values for different points along the beam. We shall visualize the shear force along the beam. We shall visualize the bending moment along the beam. What again? And we shall also determine the reaction forces at the supports. So this is the question. The question is a two-span continuous beam. It has 5 structural load on the beam: the 12 kN per meter load, the 10 kN load, the 8 kN load, and the 6 kN load. We are also told that for this beam problem, the flexural rigidity EI is equals to 100 times 10 to the power 3 kN per meter square. And we are told that there is a settlement at this support C. We are told that support C settles 4 mm downward. When you say settles, that means that support goes down by 4 mm. So we are going to model this support to move down by 4 mm. So before we move to the Ansys program, we need to determine or specify our value for E and I. E here is the Young modulus, I here is the moment of inertia. We need to know our Young modulus, and we need to know the geometric property of our beam section. That is from the moment of inertia. So I did a little calculation on the next slide on how to do this. In the question, we are told that the flexural rigidity is 100 times 10 to the power 3 kN meter square. So I wrote here 100 times 10 to the power 6 Newton meter square. So this is the flexural rigidity. So let's assume the Young modulus is 205 gigapascal. So if we assume that the Young modulus is 205 gigapascal, we can compute the moment of inertia I. What is the moment of inertia I? So we should put EI. This is EI. The left hand side is EI. So this 205 times 10 to the power 9 is the E, multiplied by I, that is the moment of inertia, is equals to 100 times 10 to the power 6 Newton meter square. So we can compute I here. Let me just show you on the calculator quickly on how I is calculated. So if I compute this, 10 to the power 6 cancels 10 to the power 6. So here will be 10 to the power 3. So I will be 100 divided by 205 divided by 1000. So I is 4.8780 times 10 raised minus 4 meters square, so which is what we have here. So having gotten the moment of inertia as this value, we can now determine the geometric property of our beam section. And so I made another assumption. You can make any assumption you like. It's just to specify what E and I is. I make another assumption here that assume the cross-sectional area is a square of length times the length. So we're assuming the cross-sectional, I'm assuming my cross-section is a square of length L. So if the cross-section is a square of length L, what is the formula for the moment of inertia of a square section? For a rectangle, it is BD cube over 12. So for a square section, it will be L over 4, L raised to power 4 divided by 12. So if we equate L raised to power 4 divided by 12 with the value of the Young modulo, the value of the moment of inertia here, we can compute our L as this value. So L gives us 0.2766030 meters. I would like my answer in millimeters, so I multiply this by 1000. So in millimeter, the length, that is the length of the square section, is 276.60293 millimeter. So now I've specified my material property E. The E I'm going to use is 205 gigapascal. Let me highlight it. 205 gigapascal. And the L I'm going to use is 276.60273. I'm using this value for my L. But I would like to calculate this L on my calculator quickly. I cancelled it. Let me do it quickly. 100 divided by 205 divided by 1000. L will be this value times 12. Find the just simple maths that I'm doing here. So this is the L value, so I'll multiply by 1000. So we have this value 276.6097. I'll keep this value. Let me copy it because I'll need it when I'm in the Ansys program. So this is my L value. I'll copy and paste the value, and I'll use it in my Ansys program when I'm specifying the geometric property of the beam section. Now we are going to move to the Ansys workbench to start our one-dimensional beam analysis. So now we're on the workbench. The first thing we need to do, we need to activate our static structural solver. Click on the static structural solver on the left-hand side of your screen and drag it to the middle of the screen. The engineering data will specify our Young modulus here. You double-click on it. Our Young modulus, as you have seen, the Young modulus E is 205 gigapascal. So I'm going to specify this value in the engineering data work environment. So what you need to do, create a new material, name it any material, call it steel. I will add this property to the steel, isotropic elasticity. I'll specify the Young modulus, but I want to enter the value in gigapascal, so I change the unit to gigapascal, enter 205. Portion ratio, assume is 0.3 value. So with this, I'll specify my engineering, material property, which I'm calling steel, 205 gigapascal with portion ratio of 0.3. That's all we need to do here. Next, you go to the geometric workflow. Before you double-click on geometric workflow, make sure you activate the line bodies. It is very, very important. Activate the line bodies, and you can leave this analysis tab to 3D. So now I'll double click on the geometric tab button here. Click or double click on it, So the space claim working environment will open now. Oh, the space claim window is active now. This is space claim work environment where we define our geometric model. I'll go back to my PowerPoint. So this is the problem. This is the problem. This is the trick of modeling this problem on Ansys. If we try to model this problem with two span, as in 7 meter, 11 meter, drawing line of 7 meter, 11 meter, we will face a lot of challenge. When you see problem like this, you model the problem, by breaking the beam system at salient points. When I mean salient point, at point of application of load. Because I have a 10 kilonewton load here, this will be a component. I'm going to model this part with a line. I'm going to model this part with a line. I'm also going to model this part with a line because there's a point load here. I'm also going to model this part as a line because there's a point load here. I'll model this part as a line because there's a point load here. So I'll have 1, 2, 3, 4, 5 lines. Instead of just using 2 lines from here to here, 1 line, and from here to here, 2 lines. So I'm going to specify 3 meter line, 4 meter line, 3 meter line, 5 meter line, 3 meter line on the Ansys program. It is best you do it like this so that I'm doing like this so that it will be easier for me to apply my load when I'm in the mechanical work environment. I can easily select the node at point B and apply my 10 kilonewton force. If you don't do it like that, it's difficult to apply the load and you might not be able to get result from Ansys. So this is the best method of modeling the problem, breaking it at salient points. So now I'll go back to the space claim working environment. Let's draw the line along the XY plane. So click on this, select this plane, click on this button, plan view, and click on the line command here. So I'll start my drawing from the 0, coordinates. Click on that point, move your mouse to the left, type the first distance is 3 meter. You see 3 meter. So that my unit for my length is in millimeter. So this length will be 3000 mm. I'm going to enter 3000 mm for the length of my line in the space claim working environment. So 3000. Press tab to move to the degree input and enter 0 degree. It is very, very important. If you don't do this, if you press enter instead of also editing that degree, you might have the degree might be off from 0. So it's very important you specify the 2 dimensions. So this is one part of the line. So zoom in, zoom out. We're entering 4 meter as the length of the next part, 4 meter, that is 4000 mm. 4 meter, 4000 mm. Press tab to move to the degree input. Enter 180. Oh, I'm always going back. We enter 3 meter, 5 meter, 3 meter as the next line. 3 meter, 5 meter, 3 meter. So 3 meter, tab 180, enter, zoom in, zoom out, 5 meter, tab 180, enter, 3 meter, tab 180, enter. So now press escape to leave the line command. So this is my finite element model, my beam system. I'll click this button to end my sketch. So the next thing we need to do, we need to define our cross section. So to do that, you click on the prepare tab. Under the beam panel, click on profile, click on rectangular profile. So doing that, a new folder will be open on the left hand side of the screen. Still trying to come on. Beam profile. So you see the section we just added, we just created. So click on it, right click, edit beam profile. And we need to edit the length and width of we need to edit the B and H of this section. Currently they are set to 10 mm, 10 mm. I've copied the value of the length of my square section. So what I need to do is just to press Ctrl V on my keyboard to paste that value. I do the same thing for the H, Ctrl V to paste the value. So you see now this is 276.6 mm, this is 276.6 mm also. So what do we need to do now? Oh, let me zoom out so I can see the section. This is the section. So we can close this section window now and click on this the structure tab here. We need to apply the section to the line segment. So click on create under the beam panel here, and you select each of the line segments to apply the beam profile. So I'm clicking on each of it now. I've clicked on the first one. Computer is not responding. Wait, why? Click on the second one. Still not responding. Click on the second one. Click on the third one. Click on the fourth. Click on the fifth. Now I've applied the profile to all my line segments. Next thing we need to do, click on the escape on your key. Press on the escape on your keyboard to leave the create function. Let's check the profile we just created, the beam section we just created. We created five beam sections. These are the beam parts. What we need to do, which is very important, we need to share topology, connect the node points together. And there are two ways of doing this. Either you click on design here and change this shared topology from none to share. I always do this, but I want to use another method to do this in this video. I think we come to the workbench. Yeah, the workbench. Click on the workbench tab and click on share. When you click on share, you see Ansys helps us connect our nodes together. So the elements are connected together now because we click on this share. What we need to do, we need to click this complete button to accept what Ansys just suggested to us. So now the beam sections are connected together and they function as a member. So now we can leave this work environment by closing the space clean working environment. Let's go back to the workbench. We have defined our geometric model now. You can move to the model workflow. Double click on this and the mechanical work environment will open. This is where we mesh our beam finite element. This is where we will apply our boundary condition, support boundary condition. We apply our structural load on the beam finite element, and we will analyze our results and also visualize our results. Now, the mechanical work environment is fully active. Under the geometry, we check, we have one component, call it one member, and that one member has 5 parts. You can see the parts. I'm selecting the parts, you can see it. So we need to actually apply our material model, that is the steel I created, to this component. Currently, the material assigned to it is structural steel. We need to change it to steel. This is the material we created at the beginning of the video. So I've changed the material assignment to steel now. So we move down the workflow. Mesh is the second. We need to mesh our model, and you should right click on it, insert, click on sizing. Under sizing, we are going to mesh our beam using geometry selection. Geometry selection. So we can select the whole body and apply geometry. So the whole body is selected. Element size. This I don't actually like this type of sizing. I don't like this type of sizing. I would like to select each element, not select the body member. So edge, select each of the elements and apply. Because we select the element, we can mesh our model by number of division. When I select the body as my geometry, the number of division was not available. So currently the number of division is 1. Each element is analyzed using one finite element. Like the one-dimensional and the truss problem, where I was using one finite element for a part. For the beam, you cannot do that. You have to mesh the beam into small, very tiny parts. This one part will not give you accurate results. Meshing each part with one finite element will not give you accurate results. You have to increase the number of division by a lot, say by 50. Then if I put 10, you see each part has 10 finite elements. But say I want it, say 50. 50 is okay to give us very good results. It's actually too much. So number of division for each part is 50. So each part has 50 divisions. That's what this means. So now I move to the static structure to specify my boundary condition, my support boundary condition. I click on it, insert. I'll use different support here. I'm going to use the simplest support, and I'm going to apply it to this node. The node here. Click on the node, the vertex selection tool here. If you check our PowerPoint, the support here is a hinge support, and this support I added here is like a pin support. So I'm going to apply this support to this node. The node is selected. Click on apply. So this support is applied to this node now. At the middle support, I cannot use this. So I cannot use this same support because we have a settlement of 4 mm. So I will specify it differently. At this support, we have a ruler support. So I cannot also use the pin support I use at A because I only have restraint in the vertical direction. So I only need to restrain the vertical direction at this support. So it means at this is the end of the beam. At this end, I can't use this support because this support restrain movement both in the X and Y direction. And I don't want that. You don't want that. So what you will do, click on the static structure. I'm going to use the displacement type of support at that point. So this is the displacement type of support. So this displacement support is already applied to this node because it was selected when I added it. So it's already applied to this node. So I want my X to be free, but my Y, I don't want movement in the Y direction. I also want my Z to be free. So I'll specify the support boundary condition at this point. At the middle, I'll also use the displacement boundary condition. I will duplicate it and I will select this node and I will apply this displacement through to the middle support. And here I can specify the settlement in the Y component minus 4 mm. So that is the support boundary condition specification at the middle support. I can decide to select these 3 supports and group it in a folder. I call it support. So what I'll do now, I've specified the support boundary condition. You need to apply your load on the beam. So click on static structure. What are the load on the beam? We have we have this part, we have this part. This part, what are the load on that part? What is the load on this part rather? Um, the load on this part, AB, is just the uniform driven load, 12 kilonewton. I'm going to apply 12 kilonewton load on this on the first part. And there are 2 methods of doing it. I'm going to show you the 2 methods. It's either you click on static structure, insert, either you use this first specification here, the first button here, and because I selected the element is already applied. The force is already applied to that element because I selected the element while creating the force, this structural force um, specification. So you will need to change this define by to component. This force specification is always in Newton, and the load we want to specify is in kilonewton meter. So we need to actually calculate the equivalent of this 12 kilonewton meter on span AB. So this is 12 kilonewton meter. This is actually 12,000 Newton meter. And we have 3 meter, 12,000 Newton meter. So 12,000 Newton per meter, and we have 3 meters. So the total load is 12,000 Newton multiplied by 3. That is 36,000 Newton. So it means that I'm going to apply 36,000 Newton force on the edge AB. So that is one method of doing it. So it means that in the Y direction, Y component, I'll specify minus 36,000 Newton. So this is one way. Another way is you click on static structure, insert, you use there is line load. The line load is not available. Or the line pressure, yeah. You specify the load using line pressure. And in the line pressure, let's select this part, the first part, apply to that part. defined by, change it to component. In the y direction, the load is specified in Newton millimeter. But let's change the unit. We can change the unit to metric unit. So now it's Newton per meter. So what is the Newton per meter load in the y direction? So we go back to the PowerPoint. The Newton per meter will be 12,000 Newton. This is 12,000 kilonewton per meter, which is equivalent to 12,000 Newton. 12,000 Newton per meter. It means that here we specify 12,000 Newton per meter minus, because the load is pointing downward. So it's either we use this or you will use this. It gives the same result. So any of the two. But I'm going to stick with the first one, so I'm going to delete it. I just wanted to show you how it is done, how you use either of the two. They give the same result. So I'll delete the line pressure because it has the same effect. So I will duplicate this force. I'm duplicating it because we also have uniform distributed load applied at BC. So I want to apply the duplicated load on BC. So I'll select BC, that's the next component. Force 2, I will apply to that part, minus 36. But the load will not be minus 36,000 Newton. The load will be 12 times 4, 48,000 Newton, because the span is 4, 48,000 Newton. So this will be minus 48,000 Newton. So these two represent my uniformly distributed load on the first span. So the point load on the first span is 10 kilonewton at this point. So I'm going to specify that load 10 kilonewton now. Static structure, insert force, but I'm going to select node. I'm going to select this node and apply that force to that node. So component, defined by component, 10 kilonewton force, that is 10,000 Newton, minus 10,000 Newton. This is minus 10,000 Newton. So those are all the load on the first span. You can select the three, you will and classify it as a first span load. Do the same thing for the second. We have 8 kilonewton load at this point and 6 kilonewton load at this point. So I'll specify that load now, 8 kilonewton and 6 kilonewton. So static structure, insert force, select, use the support node. This is the 8 kilonewton node. So I'm going to apply to that node, change defined by to component, minus 8 kilonewton, minus 8,000 Newton. I will duplicate this node, this load. I will select the next, sorry. This first one is supposed to be applied to this node. The force 4 is supposed to be applied to this node. So I've applied that force 4 to that node. This one is now our force 5. Our force 5 is the 6, is the 6. Our force 5 is the 6 kilonewton load, that is 6,000 Newton. So I'm just going to change it to minus 6,000. So these two loads are our load on the second span. You don't need to classify it, but this makes your work neat. Second span load. Second span load. So this is the specification for the boundary support and the structural load on the beam. So here we can run analysis Click on run analysis. Let's see if we get result without any error. Well, we got an error. Wow, so what are we going to do? Let's see the error. A server pivot warning or error has been detected in the ROTS degree of freedom of node 164 located in the beam. Okay, I think I know what we need to do to fix this error. We have to apply rotational restraint at one of actually we can apply rotational restraint at each of the each of the node. In Ansys, this beam element has three rotational movements in the X, Y, and Z. But I want the rotation to be free in the Z direction. What we need to do is we need to fix the rotation in the X and Y direction. That is what is causing this problem. So if I click on static structure, insert rotational displacement, click on rotational displacement. We need to restrain rotational movement in the XY direction. So we just select any node, say the first node, apply this rotational displacement to that. Under the, I want my XYZ. Uh, 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 this will be duplicating the effect of this boundary condition. Okay. I apply this rotational displacement to this node, but I have to specify 6 components. My X component, I want it restraint 0. My Y component, I want it restraint 0. My Z can move. I leave that one free. But the problem is rotation of the problem is rotation of X and Y. We need to fix it to be 0. That is the problem. So I'm going to rotation X 0, rotation Y 0, rotation Y 0 degree. Because we are using rotational displacement here, we don't actually need simply supported displacement here. So I'm going to suppress this support, so it's not going to have any effect. So this is the support I'm using at this node, and this support I restrain X, Y, and rotation X and rotation XY component and rotation X and rotation Y 0, 0, 0. So let me run analysis again. Let's see what happens. This was a wrong mark. Oh, I just knew why I'm getting an error. This remote displacement is not supposed to be remote displacement, it's meant to be rotational displacement. So I'm using the wrong type of displacement specification. So I'm going to delete this. Static structure. Instead of using remote displacement, you're supposed to use fixed rotation. This is what we're supposed to use. So I was surprised when I was seeing XYZ component because I don't normally see XYZ component. So here I will apply this fixed rotation to say this node, and I will fix I will let rotation x be fixed, rotation y be fixed, but the rotations x, let it be the rotation z, that is my bending moment direction, let it be free. So now we need to unsuppress this simply supported. We actually need it, so I will unsuppress it. So we should not get any error now. What we just need to do is we needed to fix the movement, the rotation in the x and y direction for the beam member. So you can do this for each of the node, but it is not needed. Applying to one node is just enough. I can replicate this, I can duplicate this route and apply it to each of the nodes, but there is no need to do that. You only need to apply it to one node, and we'll get. Let me run. Let's see if we'll get our results now. In Turkish, they will say güzel, nice. So now the analysis is successful. We got an error initially because we did not use our fixed rotation. So what I did here is I fixed the movement in the x and y direction. This was what was causing error. So now I specify it as fixed, that there is no movement in that direction. And I release I made rotation z free. So now we can visualize what result do we visualize in beam analysis. We want to visualize the deformation, that is the displacement in the y direction. We want to visualize the shear force diagram. We want to visualize the bending moment diagram. And to do that, using the one-dimensional finite element method, the best way to do that is actually to create a path that spans from the beginning of the beam member to the end of the beam member. So you create that path by going to the model, right click, insert, geometry. Under the construction geometry, you create a path. So this is the path. So you need to specify you need to specify two paths in the for the path, the start node and the end node. So this is the start. So I want it at 0, 0, 0 coordinates. That is at this point. And I want the end to end here, and our span is 18 meters. Let me check PowerPoint. 3 plus 4 plus 3 plus 5 plus 3. That's 18 meters. 7 plus 11, 18 meters. So that means the x is 18 meters. So this will be 18 meters. So you can see the two are shifted. So the path is spanning from this node here to this node here. So this is this part that we use to get results. This number of sample points, we can increase the number of sample points to say 100 to get better results. So I increase the number of sample points to 100. So I'll have 100 results for this part. That's just the 100 sample results. It breaks this part into 100 parts, and we get a result for at each node along that path. So now under the solution, right click, insert, deformation, directional deformation. I want this scoping method to be by path. That's why I created the path. I will select the path I just created. All bodies. Yes, all bodies. It's not selecting all bodies. Select the all bodies. Here is still yellow. It looks as if we cannot use paths to display these results. And the only way we can display these results is by geometry selection. All bodies. Change the orientation to Y, but we can also get another directional deformation result in the insert under the beam results. Okay, beam results. Okay, let's do this. Insert, and let's click on total deformation. Click on part again. Part. I'm surprised that this is not working. So surprised. So you cannot use part for this directional deformation. I don't know why. It's showing yellow that the part is not applied to it. So let's add other result. Beam result, shear force. Click on shear force. Under geometry selection, part. Under part, click on part. I can also apply part to my total shear force. That means there's actually something going on. Let's go and check the part we created. The part we specify the part using 2-point parts. Okay, I think maybe that's why we could not apply it. Let's use another method to specify the part, edge. So using the edge method, we need to select the part, the edge, and we apply our parts to the selected geometry. So this is how it is applied now. Let's see what happens. See, under the directional deformation, let's try to apply the part under the directional deformation. Part. Good. Now the geometry is no more yellow. That means the setting is okay now. So it's because we use 2-point specification, that's why we could not use the part. So we must use the edge. The part type must be edge for us to be able to use the part in this analysis result. So I've done this for the total shear. Let's change this total one. I don't want total shear. I want the shear in the y direction. So I'll change this to directional shear force. Already set orientation y direction. Parts, all line bodies. Okay. So this is the deformation result in the y direction. This is shear force in the y direction. So let's the bending moment. Bending moment results. Bending moment. Change the scoping method to parts, all line body, type, direction bending moment, orientation the z axis, bending in the z axis, in this axis here, bending in this axis. So we can view so this is the deformation result, shear force result, bending moment result. I can also view these three results in one place. I'm going to add that now. Insert, beam result. When you click the shear moment diagram, this shear moment diagram here, very powerful. Scoping method, parts, line body. Change this to directional shear moment diagram. Yeah, this you select the second one, directional shear moment diagram. This is actually what it means. Directional. Vy means the shear force in the y direction. Mz means the moment. Uy means the deformation in the y direction. So VMU. So it shows these three results in one place. So this one result is actually these three results combined. So I'm going to run analysis now so we can visualize our results. So directional deformation, this is how our beam deflects. This is deformation of our beam. This is deformation of our beam. And so let me check at support C, we apply 4 mm deformation. Let me check if this deformation at C is 4 mm. So that's our first check. So you should be able to check your result if the result is okay. So I should get 4 mm deformation at C. So let me check. At C is 7 meter from A, 7 meter. So I have a table here, the table for deformation. So 7 meters, 7 meters, 7 meter, minus 1.1307 times 10 minus 2. Why is this? So that means we have a problem in the result. The result is not correct. I'm supposed to get minus 4 mm here, and I'm getting minus 1. I'm getting minus 0.113. I'm getting a very small value here. I'm not getting 4 mm. I'm actually getting 1.1 mm, which is not correct. So let's check out what we specify as our deformation. I think we didn't apply the deformation to the right node. This is the first node here. This is our first node. This is our second node. This is our third node. We're supposed to apply this support to this node, not this node. The support is currently applied to this node, and we're supposed to apply it to this node. So let's change it and we run the analysis. So you should be able to check your results you should be able to query your results to know if you are getting, if the result is okay. So I checked like the boundary condition. I saw that and the deformation at the 7 meter is not 4 mm. So I know the result is wrong. So and I check I'll check what I inputted to see if it's correct. And I just found out that I didn't specify my support displacement properly. So displacement 2, I'm going to reapply it to this node is selected. I'm going to apply it to that node. So I've applied the displacement to this node. So I will run analysis to get another result. So now the analysis is completed. Let's check the deformation in the y direction again. I think this will be correct. Let's check the deformation at 7 meters again. At 7 meters, yes, at 7 meters we have minus 4 times 10 to the power 3 meters. That is minus 4 mm. So this tells me that the result might be correct. So you can see this is deflected shape at 7 meters. 7 meters is around this point. The deformation here is around 4 meters. You can see around 4 mm. You can see minus 4 times 10 minus 4 e raised to minus 3. So this, okay, so this should be, let me set it. This is 7 meters. So this deformation here is minus 4 times 10 to the power 3 minus times 10 minus 3 meters. That is minus 4 mm. So you can see how the beam is deflecting, and this is the deflected shape. This is the deflected shape of the beam with the imposed deformation of minus 4 mm. This is shear force diagram. Our zero axis is around somewhere here. So this is shear force diagram, and you should notice at 3 meters we have a point load. So that's why we have two shear force values here. This is our reaction point at 7 meters. This is the reaction point at 7 meters. This is a point at this is at 10 meters. At 10 meters, we should have another point load here. We should have another step here, but I don't know why we don't have another step here. So I'm querying the result again and I'm seeing a problem because I know how my shear force diagram should look. Because we have 2 point load here, I have one step here, but I don't have the same step here. That means I didn't specify the load properly. So let's check the force. Look at where this force is applied. This force is supposed to be applied at this node, not at the support, at this node. So let's reapply this force 4. which is 8 kilonewton, 8,000 newton. Let's reapply it to this node. And force 5, the force 5, we apply it to this node. Very easy to make mistake, but you should know how to query your results. I will run analysis again to check the results to see if it's okay again. The analysis is completed again, so let's the shear force diagram. This is the new deformation result, and the new at 7 meters. At 7 meters, it is still minus 4 mm, so that is okay. The directional deformation, the shear force diagram, can see the two steps. This is the first step for the point load. This is the second step for the other load. So the shear force result looks acceptable, reasonable. Let's check the bending moment result. So this is the bending moment result. At the support, zero bending moment. Yeah, it's not fixed. It's free to rotate, so zero bending moment. We have maximum somewhere at the midspan. This is at 7 meters. We have negative moment at that point. At the midspan, we have positive moment. It's maximum here. So we have this this is the point of the first applied load on the second span. This is the point of the second applied load on the second span. And this is 0. At the end, 0. You can see this is 0. We should trace it. This is 0. So we can compare our results with my finite element result from MATLAB. So let's see what we can compare with. Let me go to MATLAB. So these are our deformation results on MATLAB. The deformation result, MATLAB does not give result for rotation. So I cannot verify this minus 0.0022 and this value. The only value I can verify is this imposed settlement, this 4 mm, which I already verified. So let's leave that one. So let's check the the reaction forces for the first finite element. So the shear force at the support, this for the shear force at node 1 is 43.13 kilonewton. So let's check our results on the Ansys for the shear force. So we see the value. Ansys gives us minus 42.78 kilonewton on the table, using the table. Minus 42.778 kilonewton in Newton, but in kilonewton is minus 42.778 kilonewton. You can see the unit here is Newton. So this is minus 42.778 kilonewton, which is very, very close to our MATLAB result, 43. Very, very close. This at the bending moment at node 1 is 0, which is what we also have in our Ansys. The bending moment at this is the shear force at node 2, at the end node of the first finite element. The shear force is 50.866. So let's check this value, 50.866. This is at 7 meter, 50.866. So at this is at 7 meters. At 7 meters, we have two values because it's a reaction point. We have two values. The first value is 50.832. 50.832. 50, we can see 200. 200, 7 meters. 50.382. 50.382 kilonewton, which is the same with MATLAB. 50.86. We got 50.38. Very close. The bending moments at that node is minus 32.06. So we can also check the bending moment value minus 32. Let's see if we get minus 32 in our Ansys. So I should change this to directional bending moment at this point at 7. You can also see minus 32. So Ansys gives very accurate results. Let's check for the second span. So for the second span, the shear force is 10.36, 10.37. Let's see if we get 10.37 on the Ansys. 10.37 shear force, 10.37 Newton. 10.37, that's 7 meters. See, we get 10.36, which is very close, very identical. The bending moment is 32, we've checked that. The shear force at the end node is 3.6. So let's check at the end node 500, 3.6. It's 3.63 kilonewton. So the result is exactly the same with the manual result on MATLAB. So this is how we analyze beam problem using one-dimensional finite element. If we want to show these three results together, which is this is it here. This better visualize the result for us. I'm trying to minimize this. Oh, sorry. So this is the shear. The one at the top is the shear force diagram. This is not actually what I wanted. The one at the top is the shear force diagram. The one at the middle is the bending moment diagram. The one below is the deflection diagram, and it shows the forces at the force here. The shear force here is minus 42.78 Newton. The shear force here is 50.38 Newton. The bending moment at the maximum bending moment here is 74.41 kilonewton meter. The maximum bending moment at this support is minus 32 kilonewton meter. It shows the maximum bending moment, but let me see if I can use the probe. The probe does not work here. I can't probe other points. So this shows us the shape of the bending moment and shear force diagram and the maximum bending moment and shear force for the whole beam system. So this is how we analyze beam problem using the one-dimensional finite element. So I've come to the end of my video session now. In my next video tutorial, we are going to analyze this same beam problem using the two-dimensional finite element method. We're going to use plate element. We're going to use plate element to analyze this beam problem. Plate elements can be like the constant strain triangular elements or the hexagonal plate elements. I'm going to talk about all this in my next video tutorial. Thank you so much for watching this video, and I hope you've learned a lot. You've gained insight on how to use Ansys program to analyze structural problems. This actually forms the basis of this skill. Actually is important to understand how to use the Ansys program, and with this knowledge you can solve a more complex problem using the Ansys software. See you in my next video tutorial. Have a nice day.